What I'd like to talk to you about this evening is vector arithmetic. We've talked about the vector quantities in class. Now I'd like to talk about three different operations that we can do with vectors. We can add them, we can subtract them, and we can multiply them by a constant scalar. In particular, if I have vector A and vector B, the little arrow that I'm putting over this vector, by the way, is called a vector hat, and it just emphasizes that A is a vector quantity. Your book uses a full arrow like this. I use just the little fish hook like that. Both are recognized. This one on the bottom is a little more efficient. So anyway, if I have my vector A, and it is written in rectangular form as the x and y components, or it is written in polar form as some magnitude at some angle. What I'd like to be able to do is then to add that to a vector B, written in rectangular form like that, or written in polar form like this. And just to make it definite, in case this is a little intimidating for you, let's let A be vector 3.0, comma 4.0, which just happens to be the same as 5.0 at an angle of 53 degrees. The only way I can find that out is actually by putting it on graph paper and measuring it, which we will do in just a moment. And likewise, let's let the vector B be negative 2.0, comma positive 2.0, which is equal to the vector 2.8 at an angle of 135 degrees. And both of these are going to be in the units of centimeters. And to emphasize that they are vectors, I'll put vector hats on each one of them. And so what I'd like to be able to do now is to add, subtract, and do constant multiples of these vectors here. I'd like to know what is the vector A plus B. What does that even mean? What is the vector A minus B? What does that even mean? And what happens if I multiply A by some constant scalar C? So for example, what is the vector that represents 4 times A? Before I answer these questions in rectangular form, which is nice and easy, I want to show you on graph paper what we're talking about. So we'll get some graph paper here. And we'll put up our two vectors that we mentioned. A was 3.0, comma 4.0 centimeters. And so if I go over to here and go over 4 and up 3, like that, then I get to this vector right here. Excuse me, over 3 and up 4. I completely said that wrong. It should be over 3 and up 4 because our components are 3, just like that. And if I now measure this with a ruler that's been properly scaled, so that the centimeter markings really are centimeters, let's see if that's right. That's pretty good. And I can see that the length or the magnitude of my vector is, lo and behold, it says 4.5. It should be 5. Okay, let me check my scale here. Yep, my centimeters are a little too big. There we go. That's much better. Now when I check the magnitude of my vector, then lo and behold, it comes out to be 5 right here. And when I check the angle with the protractor, then that angle turns out to be just right at about 51 degrees, says the protractor. 53 if you do it a little bit more precisely. And let's also get our vector b on the table. Vector b was vector negative 2.0, comma, positive 2.0. Centimeters. And so if I draw that vector, that's going to be that guy right there. Now, actually, if you know your 45, 45, 90 right triangle, you can see that this guy is 2 and this guy is 2. And so this magnitude has to be 2 root 2, which is the same as 2.8. And the angle inside here has to be 45 degrees, which means that if you measure it from due east, you get 135 degrees. So in the case of special angles, such as 45 and 30 degrees, we may not need to do any protractor measuring, and that's nice, because it is a little bit time-consuming to use the ruler and the protractor. So there are our two vectors, A and B. Let me mark them. Let's mark A in red, since it's already in red over here. And let's mark the vector B right there. Okay, so let's come back now to adding, subtracting, and scalar multiplying. Given our two vectors, A and B, we would like to add them first. And the delightful news is that vectors simply add component by component. A plus B is simply going to be the sum of the x's, comma, the sum of the y's. Or in this case, A plus B is going to add up to 3 plus negative 2 is positive 1, comma, 4 plus 2 is positive 6 centimeters. And there's my A plus B. Likewise, vector subtraction works component by component, so that A minus B is going to be the difference of the x's, comma, the difference of the y's. So in this particular case, where A is 3, comma 4, here I'm shortening the precision of it, and B is negative 2, comma 2, then A minus B would be equal to 3 minus negative 2, which is 5, comma 4 minus 2, which is 2. In other words, the x's and the y's happen independently of each other. We say it like this: what happens in the x's stays in the x's, what happens in the y's stays in the y's. And this is the principle of independence. The x and y dimensions are independent of each other. Addition and subtraction both happen independently. Well, likewise, scalar multiplication in rectangular form is really easy. If I take A and I multiply it by some constant scalar C, then I'm going to get simply that constant times AX, comma, that constant times AY. So for example, if I wanted 4A, then that would be equal to 3 times 4 in the x, and 4 times 4 in the y, or 12, comma, 60. This is the primary way that we're going to be adding and subtracting vectors all year long. We're going to be doing it in rectangular form. Add vectors in rectangular form, very, very easy. Add the x's, add the y's. Subtract vectors in rectangular form, subtract the x's, subtract the y's. To do a scalar multiple of a vector, multiply each component by that scalar. It's very, very straightforward. Tomorrow, of course, we'll practice this in class. But I want to come back to the graph now and see what this means to add the x's and to add the y's. And that's going to give us a way to add vectors in polar form as well. If you think about addition, A plus B, as meaning first go to A and then go to B, then we would do that like this. First, we would go to A, which puts us to this point right here. And from that point, we would then go additionally to B, just like this. Please notice that this vector B and this vector B are the same vector B. Changing the origin of that vector does not change the fact that it is still back to and up to. Okay. So when I add A to B, or I should say add B onto A just like that, take a look at what I get. I get a new vector that I need to represent in red or something. And this new vector is the vector A plus B. And when I count its rectangular components, look at this. It's over 1, and it is up 1, 2, 3, 4, 5, 6. It is exactly equal to the vector A plus B that we got by adding the components in the previous slide there. In other words, placing these two vectors head to tail so that I'm doing one after the other and connecting gives me the exact same result as addition. And so that's how we're going to think about graphical addition of vectors. In order to add vector A plus B, we're going to place the tail of B, the tail is the back end right here, on the head of A. So the head of A is the arrow. And then we're going to connect. So our phrase for addition is head to tail. Just like that. So going back to our graph right here, if I wanted to add A and B, I took B right there, and I placed the tail of B on the head of A, and then I connected. Now it looks like I actually accidentally stretched B by a little bit. I didn't mean to do that. That's cheating. It should be the exact same B. Looks like our B was a little bit off. And that points to something about the graphical addition of vectors, and that is that the graphical addition of vectors is imprecise because you're working from the graph. So, graphical addition, head to tail, and connect. What about subtraction? A minus B is a little bit trickier. What I'm trying to do with A minus B, let me give myself some more graph paper to work with here. And I'll get copies of A and B to play with. That way I'm not stretching it. I just did. Let's try that again. Silly vector. Okay. Clone and move. There we go. Okay. So let's bring these guys down. I tell you. All right. Well, we know what that vector is. We know that it's -2, 2. So we'll create a new copy. So there's my A. And here, the new copy is my B. What we're trying to do with subtraction is to create a new vector C so that when I add B onto C, I get A back. That's really what subtraction is all about. And so I want to draw my C so that when I place C head to tail with B, I get A. And actually, with my vectors in this arrangement here, with their tails touching, I can see just how to do that. Let me draw a new vector C so that its tail is on the head of B. Now I'm going to draw B, C, and connect. B and C are head to tail. Then that is equal to A. So C has to be the difference between A and B. Well, okay. So what can we say about this? Well, we subtracted by placing the vectors A and B tail to tail. Be a tail to tail here, and we connected from B to A. Now the connecting from B to A always throws students. And for the order here, you have to get it right because B minus A and A minus B are opposite vectors. So let's see how to do this. When I write the difference A minus B, I'm going to think of it as final minus initial. And so if I think of it as final minus initial, I'm thinking of B as the initial and A as the final, and I'm trying to draw the vector that will get me from the initial, from the beginning, to the final vector right over here. So since this was listed as A minus B, I'm going to start at B and go to A, just like that. Now that I have this vector drawn, let's see what it is in rectangular components. We can count. C is over 1, 2, 3, 4, 5. So A minus B is equal to 5 in the x direction, and then it is 1, 2 in the y direction. And if I now go back to what we got on the other page, we can see that this is exactly equal to the difference that we got by subtracting components there. So let's summarize our addition and subtraction. Addition, place the vectors head to tail and connect. Subtraction, place the vectors tail to tail and connect from the initial to the final, from B to A. Well, the last thing that we want to do is scalar multiples. And a scalar multiple of a vector C times A represents a stretch of that vector by a factor of C. Now that only makes sense if C is greater than 0. So let's consider what the vector 4A might look like. Let's take A and make a copy of it. And pull it down to here, put it right there. And if I want to now stretch my vector 4A by a factor of 4, then what I have to do is to take that vector and make it 4 times as long without changing its direction. So here we go. We're going to make it 1, 2, 3, and 4 times as long. Ta-da! There it is. And when I count that, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 over. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Should have been 16, but because I was doing it graphically, it was a little bit imprecise. I probably changed the direction a little bit by accident. Notice that 12, 16 is right here. Just like that. Okay, so that's stretching by a factor of C. Well, what if C is equal to 0? If C is equal to 0, then 0 times A for any vector is simply going to give us a 0 vector, a point, because I'm taking that vector and I'm zeroing out its magnitude. I'm giving it 0 length. What if C is less than 0? If C is less than 0, then we're going to adopt the convention that this refers to a stretch by a factor of the magnitude of c, but also a reflection. So that if c is less than 0, it flips the vector by 180 degrees. So for example, negative 2a would represent taking my vector a right here and stretching it by a factor of 2 in the opposite direction. So there's negative a, well, let's get that right. It should be over 3 and up, down 4. Here it is, negative a, and now negative 2a, just like that. So negative 2a has twice the length of a, and now it points in the opposite direction. Well, this is a lot to digest, and tomorrow all that we're going to do is to practice doing these graphical and algebraic additions of vectors. I hope you agree with me that it is much easier to add and subtract and do scalar multiples in rectangular form than it is to do adding and subtracting and scalar multiples in polar form. Because in polar form, I don't have a choice. I have to do graphical addition. Because, I'll say this very emphatically, for vectors in polar form, a plus b does not mean adding magnitudes and angles. Does not mean adding magnitudes and angles. Unfortunately, you have to use graphical methods. At this time. On Wednesday, I'm going to teach you how to convert vectors in polar form into rectangular form so that we can take advantage of our arithmetic. But for now, if you have the vector 5 at an angle of 10 degrees, and you need to add it to the vector 10 at an angle of 20 degrees, then please refrain from just trying to add the magnitudes and the angles together to get 15 at an angle of 30. That's wrong. Why? Well, let's do a quick sketch. 5 at an angle of 10 is going to be something like that. And 10 at an angle of 20 is going to be twice as long like that. And if I'm going to add them, I have to place them head to tail to make a triangle. And when I make that triangle and I connect, it should be really clear that the length of what I get here is not going to be 15. If this is 5 and this is 10, then this length right here has to be less than 15 because it is the other side of a triangle. And likewise, the angle that I measure right here is not going to be 30 degrees because I did not take the angle of this guy and add it to the angle of the other there. So please understand that when I am dealing with vectors in polar form, I cannot just go adding magnitudes and angles. That will get me the wrong answer almost every time. The only